So, welcome everyone. Thank you for joining us
Please
for
begin.
today's webinar. Hello, sir. Should I start?
Yes, sir.
Yes, please.
Okay. Welcome everyone. Thank you for joining us for today's webinar. I am Vishaka Khambati, Faculty of Biomedical Engineering Department at PITDS, Parul University. Today we are presenting a webinar on biomedical sensors and transducers, which is presented by Dr. Vipul Esha. Currently, he is working as a professor and head of instrumentation and control engineering department at Dharamsey Desai Institute of Technology, Nadia. So audience, if you have any questions during the presentation, please send your questions to the given WhatsApp number, that is 94297 Again, I repeat my number, 94297 So we will discuss it at the end. So without taking too much time, I will hand over today's session to Dr. Vipul sir. Sir, please continue.
Good afternoon, respected sir, madam, faculty members, and students. I hope you can see the screen. Is it visible, sir?
Yes, sir.
Okay.
Yes, sir.
So today's webinar is on biomedical sensors and transducers. We will cover basically the difference between sensors and transducers, types and characteristics of sensors and transducers. We have several measurement of various signals like electrical, mechanical, thermal, chemical, magnetic, vibration, sound, images, etc. Using sensors and transducers, how we can utilize them to measure those signals that we'll see, and then how to convert them and how to achieve our goal for measurement and processing of that. So basically, our human body is consisting of various organs and various structures like bone structure. Then we have various organs like heart, lungs, brain, kidney, skin, eyes, nose, ears, nails, the spinal cord. Then we have muscles. Then we have blood and blood cells. So our human body is a very complex plant, we can say like this. And multiple parameters are there which we have to monitor in our human body. Then we have to sense them. We have to achieve those signals from various body structures or organs, and then we have to convert them into the form which we can read and treat a patient accordingly. So our human body can have several open loop conditions, closed loop conditions. Basically, in open loop condition, we have input, plant, and output. In a closed loop condition, we have input, plant, output, and feedback. So that feedback comes from our human eye, and main processing element is the brain. So how the brain activity is done, how we can sense those activities, how the heart activities sense, how the kidney activities are sensed, how we can sense their different structures, its breaking conditions, muscles, contractions, expansions, etc. That is what we can have it using those sensors and transducers. So basically, you should know what is a transducer and what is a sensor. And then the difference between these two we will see, and then we'll see some principles on which the sensors are based, the transducers are based, and then we'll see how to implement them to monitor and control our human body parameters. Now, as and when say that transducer characteristics, first you should know the definition of a transducer. So transducer converts one form of energy into the another form of energy. Say for example a microphone, then microphone converts sound energy into the electrical energy. A speaker converts electrical energy into the sound wave. So this is a function of transducer which converts one form of energy into the another form of energy. So this is a part which you have to remember as a transducer definition. Then what is the sensor that you should know, and how it differs from the transducer. So sensor is that part where we are using it to convert that mechanical, thermal, chemical, or various electrical activities changes into its equivalent form like voltage, current, etc. So sensor will have the sensing part only, and transducer will convert one form of energy into the another form of energy. So we can have the conversion of mechanical energy, we can have the conversion of thermal energy, magnetic energy, chemical compositions of our human body, or various signals which are there in electrical in nature, like resistance, inductance, capacitance, that we can change in terms of voltage and current. So sensors will just sense the signals. It may be of any nature, mechanical, thermal, magnetic, chemical, electrical, etc. While transducer will convert one form of energy into the another form of energy. We shall focus on a few sensors like temperature sensors, light sensors, strain gauges. There are so many other sensors based on the requirements of our human body, like smart sensors, infrared switches, RFID, etc. So we'll begin with the electromagnetic radiation spectrum first. This spectrum is most important for us. Here we can see that complete spectrum with its range of operation. The visible light wavelength is in between 400 to 700 nanometers. The short wavelengths for ultraviolet is around 100 nanometer. The X-ray is around 1 nanometer. Gamma rays are around zero point 0.1 nanometer. Long waves like IR, it has near, thermal, and far ear ranges, which is around 1 millimeter, 100 micrometer to 1 micromillimeter range. Then we have microwave range around 1 centimeter. Radar is in between 1 to 10 centimeter. TV and FM radio signals are in between 1 to 1 meter, and AM is around this. So basically, our human body has a visible light wavelength. So as and when the light focuses on a specific object, it is reflected back, and our human eye is recognizing that object. Like this, if we have other sensory organs, right, then we can sense those signals. Say, for example, we can see certain objects, we can listen to certain sounds. So each has certain specific range of operation. So this particular spectrum is very helpful to us. That is called electromagnetic radiation spectrum. Within this range of operation, we have various sensors and transducers. Using them, we can generate certain signals, we can sense certain body parameters, and then we can convert back into our requirements. So this electromagnetic radiation spectrum is most important for us. We will see the applications of various sensors and transducers based on this particular spectrum itself. It may be within ultraviolet range, X-ray, visible light range, IR range, even radar and AM radio, FM radio, etc. Now we'll start with the temperature sensor. So when we call about that temperature sensors are available in terms of various range of operations. They are basically thermocouple, RTD. RTD is nothing but resistance temperature detector. Then we have thermistor, monolithic IC sensors, thermometer, which is our normal thermometer used by our doctors. The thermocouple has a characteristics. It has most common sensor, which is utilized for higher temperature measurement. While human body temperature is being measured by thermometer normally, it may be an analog thermometer or digital thermometer, or it may be used thermistor in it, and then we can utilize that thermistor based application for our human body temperature measurement. We can use the monolithic IC sensors. Ready-made ICs are also available, and we can measure the human body temperature. Those thermocouple and RTD are for higher temperature measurements. We will see the thermocouple principle, its construction and its characteristics first. Then we'll see the resistance temperature detector, and then we'll see the thermistor and its application. So basically, these are the temperature sensors which are utilized in industry as well as in the biomedical applications for human body temperature measurement. One of them is thermocouple. The characteristics of thermocouple are it has a pair of dissimilar wire. It is welded together at one end, which is called a sensing end or measurement end. The other end is kept at 0 degree or reference point normally, and it can be used under extreme conditions also. So if you want to measure the hard temperatures range wise, then you should go for the temperature sensor as a thermocouple. Here I have specified certain advantages and disadvantages along with its ranges. So some of these common temperature sensors are thermocouple, RTD, thermistor, and ICs. Thermocouple is self-powered. It is very inexpensive. It is a wide temperature range. It can be utilized in the range of -270 to plus 2000 degrees Celsius value of temperature. RTD, resistance temperature detector, is most stable. It is most accurate. So if you want an accurate reading, we should go for the RTD. It is expensive and current source is needed for measurement of this signal. And range of temperature is -200 degrees Celsius to 800 degrees Celsius. Thermistor has high output. It is fast and inexpensive. It gives us very non-linear graph. That is only the disadvantage of it. So we have to utilize the linear portion of our thermistor for measurement of our temperature. And it falls within the range of -80 to plus 150 degrees Celsius. So within this, we can measure the human body temperature. Certain ICs are there, which are integrated circuits, where we need some power supply as a source to activate those ICs, and then we can measure those degrees Celsius temperature below 200 degree Celsius reading. Now coming back to the temperature sensor as a thermocouple, here you can see this thermocouple which is having two different metals, metal A and metal B. There is a hot junction where metal A and B are connected together. And there is a cold junction or a reference junction where another junction is prepared. So this particular hot junction or measurement junction is utilized for measurement of the temperature with reference to this cold junction. So for this you need a cold junction compensation circuit, or you keep this in an ice bath permanently at 0 degrees Celsius. Now with reference to this 0 degrees Celsius, we can monitor the change as in when it occurs at this particular measurement junction. So this is called a measurement junction. As and when the heat is applied at this point, that temperature will change. It is due to the change in the current. So milliampere current will be flowing through this two wires. These two wires are different together. Both of these wires, metal wise, construction wise, they are different. So you can use the copper as a positive element of it and constant as a negative element of it. One is a positive metal, another is a negative metal here. And then the output of this can be a millivolt, milliampere signal, which can be further amplified. So this is your measurement point and this is your reference point. With reference to this reference point, we are measuring the thermocouple's change in the temperature. So these are the various metals and alloys which you can utilize for this various types of this thermocouples. Type E, J, K, S, and T are the common thermocouples type. It has a various range of operation. For example, chromal constant, iron constant, chromal eliminal, platinum, rhodium, copper constant, etc. So when you say type E, the alloys utilized for this temperature sensor is for chromal as well as constant. So chromal will be a metal A, which is utilized here as a positive metal, and constant is our negative metal. And based on this equation, we are generating that voltage. So millivolt signal is further amplified when this measurement point is heated. Difference of millivolt will be generated between metal A and metal B. For example, if we have a type E, then we have metal A as a chromal and metal B as a constant material. We can utilize this type E within the range of -270 degrees Celsius to 1000 degrees Celsius. So any temperature within this will be very easily readable using this thermocouple type E. And it will generate a millivolt signal as a output of this. This millivolt signal we can further amplify and we can utilize that for this voltage measurement purpose. And using that voltage, we can convert back into the degree Celsius temperature. So we have to set a relationship between this voltage, which is generated here in terms of millivolt initially, which is amplified further, and then it should be converted back into our degree Celsius temperature. So as and when the measurement point is heated, this temperature is rising or it may be falling from the current value. So appropriate millivolt signal is generated, and that millivolt signal we have to amplify further, and then we can measure the degree Celsius temperature. Other metals can be utilized for different types of thermocouple, like thermocouple of J type can have ion constituent. So ion will be the positive metal, metal A, and constituent will be the negative metal, metal B. So this way you can have the thermocouple application. The thermocouple will give you the millivolt signal as the output, and within the range of its conditions, we can measure the millivolt signal. That millivolt signal we can further expand with the amplifier, and then we will get the voltage as an output. So this way you can measure the temperature. This is the ice bath where reference junction of our thermocouple is kept constant. This is copper metal. This is a constant in copper. So plus is a metal A, minus is a metal B. This is the measurement junction where heat is applied. This is that reference junction, which is normally the ice water bath. Here we are keeping this point at 0 degrees Celsius. Now what will happen that temperature is increasing here. So appropriate millivolt signal will be generated, and these are the two lead wires which has a 0 voltage, almost 0 voltage, and whatever millivolt signal is generated here, that you can measure here. Further we can amplify it, and then we can have the converted signal into the voltage form. So whatever temperature is there, we can have the equivalent voltage here with reference to this 0 degree Celsius. So this 0 degree Celsius is our reference. This reference should be compensated, or it should be there in the ice water bath. So this will be at every time 0 degree Celsius. Now whatever temperature change is there, based on the range of your two metal wires which you are utilizing here, the millivolt signal will be generated, and within the range of that operation we can have the voltage as an output. So this is how your temperature sensor thermocouple works. Now as and when thermocouple gives you the output, you should carry it to the remote location also. So for that remote location transfer, we are utilizing the reference wire, which is a manganese wire normally. So suppose there is a range of around 20 meters distance between your specific point, which is a measurement point, and your control room here, then you should have that wires extension. So these are the two wires, metallic wires, which have the 0 resistance normally, and whatever signal is generated in terms of millivolt here, that will be readable at your reference point in the control room. So this is how you can utilize this temperature sensor as a measurement of our human body temperature. Then you can have the junctions. They will be at the point of the short, or temperature readings will be incorrect if it is shorted wire. You have to take care of these problems as and when it occurs. So normally whatever we have seen is your open loop system. Now within that open loop system, if you apply the feedback with reference to this measurement point, you can generate that at degree Celsius temperature. You will have some set point value. With reference to that set point value, if there is a variation, you can monitor and measure that value, and then you can apply those feedback signal so as to complete the loop. You can control this temperature as well. So basically you have to remember that calibration part of it. For that we have seen what is to be done. For calibration portion, we have this reference point as a pole junction compensated point, which should be kept at 0 degrees Celsius. If you don't compensate this point, every time this point should be at 0 degrees Celsius. If you don't keep this as a 0 degrees Celsius, your temperature measurement will be wrong. You should have a compensatory circuit here, or you can keep it in an ice bath and maintain this 0 degrees Celsius. Now every time it will be measurement points value which will be changing with reference to 0 degrees Celsius. So this is what you have to take care as an analysis part of your thermocouple. Now we will see some different types of thermocouples, which are mentioned earlier. This is those figures of those sensors which are utilized as a thermocouple. Basically, you have to remember the signal should be received by you in a proper fashion. The lead should be in such a fashion that it should not be added with its own resistance. Otherwise, the temperature which you are measuring at the remote location is different. So you should have the proper selection as per the range of operation. In terms of human body measurement, we can go for thermocouple within the range of 0 degrees Celsius to maximum 50 degrees Celsius. Another sensor which we can have in this range is a resistance temperature detector. As the temperature of a resistance increases, so does its resistance. So this is the main idea behind the resistance temperature detector. Resistance temperature detector is known as RTD. RTD is another temperature sensor within the range of 0 to, say for example, 650 degrees Celsius. You can utilize this RTD for measurement of temperature. In this RTD, you have certain resistance which is made up of platinum, copper, etc. And as and when you heat one end of this metal, it will generate a change in resistance. You can measure that change in resistance by applying this in one arm of a Western bridge circuit, and then you can measure the effective temperature. So basically, in this resistance temperature detector, which is recognized as a RTD, we are having the change in resistance, and that change in resistance is equal to change in temperature. So as and when temperature increases or decreases, there will be the change in the resistance accordingly. If temperature increases, resistance will increase. If temperature decreases, resistance will decrease. And it is most accurate, so better you go for the accuracy in your measurement. Now, one of this industrial utilized RTD is PT100. So PT100 will give you 100 ohm resistance at 0 degrees Celsius. This is the most common resistance temperature detector. As a metal of this, we are using this platinum. PT means platinum and 100 means platinum is a material which is utilized here as a sensor to measure temperature. It will give us 100 ohm resistance at 0 degrees Celsius temperature. That's why it is called PT100 resistance temperature detector. This is how you can measure this temperature using RTD. I have shown you that RTD bridge circuit. These are the three different arms of your Western bridge. The fourth arm is consisting of that RTD, which was mentioned here. So whatever RTD you are choosing, that is kept in this fourth arm. So this is that RTD, resistance temperature detector. And now your bridge circuit is completed. With reference to this applied input, you can achieve that output between these 2 points of this Western bridge. So as and when you heat that sensing point of this RTD, the change in resistance will occur. That change in resistance you can achieve through this Western bridge circuit as a change in the voltage, and that voltage equivalent change you can monitor in terms of degrees Celsius temperature. So whatever changes are occurring at the measurement point of your RTD, you can convert that into the equivalent circuit of your resistance. The change in resistance is again measured in terms of voltage, and that is how that voltage can be converted back into the readable form of our temperature. So this is how that bridge circuit is working, and RTD is kept in the bridge circuit. For this application, you require that input source. So this is your input source. These are the known resistances which are there in the 2 arms of this Western bridge. This is for balancing purpose, and this is that actual RTD sensor. Through this sensor, we can measure and monitor that particular temperature. And it is very accurate reading, which you can have it using RTD. Voltage across RTD rises, the resistance increases with the rise in temperature. The constant current also increases the temperature of the resistance and affects the temperature reading. So this is how your RTD will work. Then we have another temperature measurement sensor, which is called thermistor. So what is thermistor, how to utilize that, and what is the range of operation for that thermistor? For our human body temperature measurement, we can utilize this thermistor. or we can go for the thermometer, or we can go for the monolithic IC, which is ready-made available in terms of IC, integrated circuits. So thermistor is one of this sensor which is utilized for temperature measurement, resistance of which is having high negative temperature coefficient of resistance. So some of these thermistors which are utilized for human body measurement purpose are having high negative temperature coefficient. So resistance will decrease with increase in temperature. Earlier we have seen in the case of RTD that as and when the temperature increases, the resistance is increasing. But the property of the thermistor here is the resistance with high negative temperature coefficient. So as and when the resistance decreases, it increases the temperature. This is for thermistor. The high temperature coefficients means that there is a significant change in resistance for a small temperature change. So it works within the 0 to 55 degrees Celsius, say for example, or even less based on the material of construction. So change in the resistance for a small temperature change is possible to measure using thermistor. It may be in terms of semiconductor material, which is utilized for construction of this thermistor. It is either in tube form or Bates slips. It comes in the wide range of values. Also, it comes with manufacturer provide resistance versus temperature curves. So as and when you purchase this thermistor, the ready-made solution is there for resistance versus temperature curves, and you can utilize that as per your requirement in your human body temperature measurement. So this is a typical curve which is for a specific thermistor. It also comes under the manufacturer provided resistance versus temperature curve. So sample for thermistor with nominal value of 5 kilo ohm at 0 degrees Celsius is maintained over here. And this is the temperature graph as and when resistance is changing. So it is having a negative temperature coefficient for resistance. So as and when the resistance increases, the temperature will increase. If resistance is increasing, temperature will decrease, and so on. So monolithic IC is the fourth sensor, which we have to see them as a temperature sensing devices. So you can utilize those integrated circuits. This is that specific IC sensor, which can be utilized here in the voltage divider circuit, and we can measure the voltage change, which will be equivalent to the change in the temperature. This gives us a linear output voltage or currents with the temperature changes. So what is the meaning of it? As and when you keep this IC sensor, as and when you keep this IC sensor at the point where you want to monitor and maintain the temperature change, it will change as the voltage or current, and then voltage or current can be monitored and controlled through this voltage divider circuit. So you can effectively calculate what will be the V out here of your voltage divider circuit, provided that you have these two arms, and in one of this arm you are keeping this IC sensor, and the arm is known as a resistance, which is known to you ahead of time. So you can calculate what will be the voltage output here as and when the temperature changes here. So as and when the IC sensor will be sensing that change in temperature, the effective resistance will change here, and effectively you can change this voltage over here. That will be the, in terms of degree Celsius, you can convert later on. Some light sensors are also there. Typical uses of these light sensors are to measure the intensity of the light and to detect the presence of or absence of a light. Other light sensors are also utilized as a photovoltaic cell, photoconductive cell, photodiode, phototransistors, etc. We have some semiconductor material that can generate a voltage when light shines or imparts on it. We have a light sensors like this, which are made up of photovoltaic cell, and as and when the light is falling on it, it will measure the change in this light itself. So it will detect the light. It will have no detection if light is not present, and that intensity of light can be converted back into the temperature. So this is the internal construction of that light sensor, which is utilized here as a photoconductive cell. There is an electrode. The cold wire contacts are here. Then you have a ceramic material sheath over here, two wire terminals, photoconductive material over here at the top surface. This is the photoconductive material. Then there is a second electrode, and then there is a coating. So metal contacts with external connections. This thin film have a high sheet resistance, This has a high seat resistance. Therefore, the shape between the two contacts is made narrow, and it is a long cell resistance at a moderate light levels. So as in when the light imparts here on this, it will change its resistance. And that is what we are monitoring and controlling. And then after, we are converting back into the temperature. So light will fall, and then we can have the open base circuit. There is a photoconductive cell in this as a resistive. Light will fall here. This is another known resistance. This is the open wave circuit from which we can have the analog output over here. So this is how we can utilize that photoconductive cell. As in when the light imparts here, this photoconductive cell, which has the construction like this, will have the light imparted on it. This light has a minimum to maximum intensity of it that can be measured here. Now, further, we have this circuit, which is open base circuit, through which we can monitor and control whatever change over here occurs in this light, which is falling on this particular photoconductive cell. And finally, we can generate that voltage as output signal, which can be calibrated in terms of that temperature or light source itself. There is another circuit through which we can monitor and maintain this light sensors. This can be applied to the microprocessor based system here. Say, for example, if you want to convert that and we can have the display of it. So this is my analog circuit. We can have the analog to digital converter of this voltage output. So we can provide one ADC circuit here, which will be converting this voltage into the digital signal, and then we can apply it to the microprocessor based system. So that will become our complete closed loop arrangement, and we can have a feedback from our microcontroller based system so as to monitor and maintain this light source as per requirement. So we can change this light source as per its angle, its location, and we can monitor and maintain this temperature with reference to this change in the voltage. So this voltage is analog voltage. Further, we can process that with reference to that analog to digital converter. Analog to digital converter is needed for conversion into this digital form, because our majority of the microprocessors and controllers are achieving only digital inputs. So those outputs which are in terms of voltage signal are analog in nature. Here we can apply the A to D converter, and through A to D converter we can convert that signal back into the digital form. Now it is appropriate for our microprocessor or controller, and then we can monitor this light which is imparted on this particular photovoltaic cell. If we have a feedback, we can control this light source also, and we can monitor and control that particular light sensor's activity through the microprocessor based systems. So these are some of these critical aspects which you have to remember as a basic command for measuring the RC delay time or contacted circuits, and you can utilize this for the temperature transducers. Then we have photodiodes. This is the circuit for a photodiode. Here, a diode is a forward bias diode. You can see here that is in the green color. Light is falling on this photodiode. Very fast reactions to the changing light levels are occurring, and here we can monitor this particular voltage as an output. So as and when the light imparts here on this photodiode, its forward bias condition will occur, and you can monitor this output over here. So with various conditions of this light, you can have various output voltages in terms of 0 to 5 volt outputted over here. That is with reference to this change in the light source. So it has a very fast reactions to the changing light levels. Same physical size as LEDs. This is a diode, photodiode. So it is a very small component which you can utilize for your light sensing purpose. It has a small window through which light is sensed. So on a photodiode, if you have seen that, very small window is there from where the light is imparted on this, and then there is a change in resistance which is occurring on this material. There is a known resistance, and you can generate a differential voltage over here. Through this, you can achieve this output. So high resistance is readable over here. The resistance will drop significantly over the period of time. So there is only limitation of this. Usually used to utilize the low levels of light. Light sensors as a phototransistors are also there, which can be worked within the range of 30 to 50 volt maximum collector to emitter voltages, and maximum collector to current is 25 milliampere current. So phototransistors, you can utilize light sensors. Conductive materials, you can utilize. Photoresistors, you can utilize as a light sensor. As a light sensor, replacement considerations are also possible. You can choose your best option in an exact replacement. If not possible, match the following characteristics and then choose the light options. So it can be specified in terms of nanometer, which is within the range of human sight, or it may be 700 nanometer, which is a red light. So different colors you can impart on this as per your requirement, and you can sense this. So by imparting the infrared lights, you can monitor and maintain the blur flow, blur volume, etc., blur color and compositions, etc. Light intensity will change with reference to this coordinates x and y of your photoresistance, and then you can monitor and maintain that change in the resistance, and that will be effectively as per the change in the light source itself. Other sensors which are utilized for this is burnout, weak or obstructed light sources, which may create a problem for you. Light shields may have a misalignment by a lens, so you can have a proper calibration. So that is the only limitation with the light sensors which you are utilizing. You have to have a proper calibration. You have to have a proper installation first, and then you can utilize them for the measurement purpose. Some mechanical sensors are also there, which are utilized for the purpose of force, motion, position, etc. Now, some mechanical sensors can measure force, some can measure the motion, some can measure the position. So where we can apply this? So basically we are using the strain gauges for this mechanical measurement purpose. Strain gauges, we will see in detail what is the mechanical arrangement of it, how it is constructed, what is the bonded strain gauge, unbonded strain gauge, where we can utilize in our human body purpose. So you might have heard about muscle contraction and expansion. That muscle contraction and expansion is based on the force, and motion will occur based on the force activity, and you can have certain positions measured for this particular activity. So for that purpose, we are utilizing the strain gauges. The purpose of the strain gauges is there is a specific wire, a specific material is used for strain gauge material. This wire will have the elongation or expansion. Expansion or contraction in it will occur as and when you apply certain forces. So when the forces are in opposite direction, it is expansion. When the forces are in opposite direction towards outer way, it is expanded condition of it. When you are applying the forces in the opposite direction towards it, both of them are there towards the center of the material, it will create a contraction. So this is the principle on which the strain gauges are utilized for measurement of strain. So sensors used to measure change in the dimensions of solid objects caused by the force. So this is the material which you can see like this, which is of your strain gauge. This is the stretch condition of it. This is the original condition of your unstretched material, which is utilized as a strain gauge. You assume that there is a fixed base, and with the fixed base, you have this strain gauge connected. Now, this is the normal position of it with the length L, you can say like this, or L0. And then you are expanding this with the application of force here. Due to this force, it is expanded by delta L length. So the complete material is expanded just like your rubber band, right? If you expand this by applying the force, that rubber band will change its length. So this is your normal length. This is the expanded length when you apply this force. This is the fixed base with which you have connected this wire, and then you are applying this force. So this was the original condition of your strain gauge material wire, and then this is the force condition. You are applying the force towards outer direction, and this end is fixed. So if you apply the force like this particular edge will be expanded by this much distance. That is called delta L value. So L0 will become L0 plus delta L under the influence of this force. And we are measuring this strain with reference to this delta L divided by L0. So what is this delta L? Delta L is a change in the length due to the force. So whatever force we are applying on this original material of wire, that is occurring in this much deviation. So this much length is increased of this wire due to application of this force. And how to measure from this that strain which is occurring, that is through delta L divided by L0 equation. So what is L0? L0 is the original length of this conductor which is utilized as a strain gauge material, and we are dividing that delta L by this particular length, original length. So this is the unstretched bar which is having length L0, and this is the stretch condition of this bar. Same bar is applied under force, and due to this force applied in this direction, it has a change of delta L. Now this strain will be nothing but delta L divided by L0. So whatever is the original length you are having, that is L0, and whatever change in the length is occurring due to the force application, that you are measuring. So once you measure both these terms, you can divide that delta L by L0, and that is called our strain. So this is what our strain gauge will measure as a part of our strain. This is nothing but a force which we are applied, and that force is measured in terms of delta L divided by L0. So expansion or compression, same way you can expand this by applying more force towards this direction. If you apply force in this opposite direction, what will happen? The material will contract. So both tension and compression forces you can apply here, and this material will have the expansion or compression accordingly, and based on that the variations in the strain can be measured. Through this you can measure the stress of your muscle. So whatever muscle activity is there, for that you can utilize this strain gauge. Now in the strain gauge we have seen that it is delta L divided by L0, where delta L is a change in the length of the force due to application of force, and L0 is the original length before the force was applied. The force can be expanded direction, force can be in the contracted direction, and the stress is measured by force upon area, that is cross sectional area. So each material of construction is having this cross sectional area, so that is also important, the material which you are utilizing for strain gauge and the cross section area of this particular wire which is utilized for the strain measurement. And based on this you can measure the stress as force applied divided by cross sectional area. This is another formula through which you can measure the stress or strain. The resistor conductor can be determined from R is equal to rho L divided by A. This is for strain and stress conditions. The resistance conductance can be determined by this formula R. R is what? Resistance. Change in resistance occurs in terms of ohm. Rho is the resistivity of the material which you are utilizing as a strain gauge material. Capital L is the length of the conductor of this material, and A is the cross sectional area of this material. So resistance can be measured in terms of this, and this strain gauge, if you keep it in the Western bridge, you can monitor and maintain this resistance through the Western bridge circuit. So effectively you can measure the stress and strain which is occurring in the muscle expansion, contraction, etc. So all muscular activity you can monitor and control using the strain gauge utilized for this particular purpose. Basic equation for strain gauge is R is equal to rho L divided by A, where R is the effective resistance which you are getting from the stress or strain. It may be through the expansion or contraction of this material. Rho is the resistivity of the material itself, which is utilized for the construction of the strain gauge. Capital L is the length of the material which is initially utilized by you before you apply the force. So unforced condition, you have the material of construction that has certain length, that has certain cross sectional area, which is capital L as a length and capital A as a cross sectional area. If the gauge material under stress increases its length by 0.4%, its resistance will increase by 0.4%. That is the normal equation which you have to remember for measurement of this. And then the material of semiconductor foil woven on a back or forth to increase the length can be utilized for the construction of strain gauge. The range of common values are between 30 to 3000 ohm. The most common value size falls within the range of 120 to 350 ohms. This is how you can utilize the strain gauges in terms of Western bridge circuit. So earlier we have seen that how to utilize that resistance temperature detector, which is my RTD using the typical bridge. So this is the bridge circuit. Using this bridge circuit, you can utilize the strain gauge measurement also. You can have the metal beam and force can be applied like this, and this you can convert back into the change in the voltage or resistance. So effectively you are applying this force here. This is the fixed edge, and metal beam is expanded or contracted by application of this force. Now this particular arm or this particular arm, or in this figure if you see this, it is an arm of your Western bridge. This arm of a Western bridge, one of this arm you can have it as a strain gauge. Whatever stress or strain you are applying on that particular material of strain gauge can be having the change in the effective resistance here. Overall change in the effective resistance will convert into the effective voltage as an output. Again here you need a voltage source. So it is a passive circuit for which you are utilizing the strain gauge as a material of construction. So as in when you apply force here on that material, that change occurs, that change in the wire length, change in the cross-sectional area, etc. You can monitor and measure. Effectively, the resistance will change. The change in the resistance will monitor and maintain through the change in the output voltage. So this is how you can measure the mechanical force occurring at any muscle. Now, these are the typical strain gauges which are shown here in this figure. It is with bonding conditions, certain are with unbonded conditions. So this is that material of constructions. Wire are kept like this in a zigzag fashion, and bonding is done through this. And these are the lead wires through which you can expand this. And these wires you can connect with the edge of your Western bridge. So this is the construction of this strain gauge. This is how various strain gauges can be connected, multiple strain gauges. This is a single strain gauge. This can be available in terms of bonding conditions or unbonded conditions also. So strain gauges are available in terms of bonded as well as unbonded conditions. Few smart sensors are there which are available. Primitive sensors are devices or materials that have some electrical property that changes with some physical phenomena. We can have the ultrasonic distance detector. We have seen that range of various light sources, right? Various waveforms. One of this waveform is the ultrasonic range. Within that, this sensor will work. So you have a source and a detector. The different objects, and that is received over here. So you are measuring effectively the time duration through which you are measuring distance traveled by the ultrasonic sensors. That ultrasonic light waves will have the various traveling conditions as and when you keep it in a different material. It may be air as a medium, it may be water as a medium, it may be any other medium. The ultrasonic rays will pass from it. You are detecting through the detector at the other end, and you can monitor and maintain the effective timing, and you can calibrate that for your own purpose. So this is how you can measure and control the ultrasonic detectors distance, and then distance can be calibrated in terms of your measurement quantity. So this is that ultrasonic sensor which will sense the echo back conditions of this. So rays are sent. This is an object. It will reflect this back. So total time of travel will be measured. And then you can control that. You can easily monitor and maintain this. So this particular principle you can utilize for kidney stone analysis, where rays are sent on a kidney uh, area, effective area, where stone is there, and the rays will be reflected back from the stone. You can measure and monitor the effective timing here. You can calibrate in terms of that, and you can detect whether the stone is there or not. Ultrasonic detection is utilized for human body purpose, fetal monitoring purpose also, where you can monitor the presence of baby. Then certain parallax error you can remove. Before that, you have to see that how the measurement is done and within which range it is done. Some of this other sensors are falling like accelerator. Accelerations are utilized for speed measurement. So as in when you want to measure the speed, you can use the accelerator. Accelerations are for measurement of tilt angles, inclined angles, rotations, vibrations, collisions, gravity, etc. Accelerometers are already used in many different devices. These include personal electronics, specialized equipment, and machines. Here are just few examples of it: self-balancing robot, tilt mode game controllers, mode airplane airplanes, car alarm systems, human motion monitoring system. So each human motion you can monitor for this particular purpose. So accelerometer will measure what the different conditions, tilt angles, rotations, vibrations, collisions, etc. So if you want to monitor and maintain the human motions, suppose a particular person is having that accident, and after that you want to monitor and maintain its activity. What is the motion activity, right? Before falling condition, before normal conditions, etc. Then you can monitor this using the accelerometers. Then you can utilize the RFID. RFID is a most common definition nowadays. Radio frequency identification is an automatic identification method relying on storing and remotely retrieving data using devices called RFID tags or transponders. So, as in when you have some samples, if for example I'm collecting various patients' various data, and some samples are also to be tested. So you can provide this RFID tag to each and every samples of a different patient data monitoring system. So you can have some blood sample, you can have some urine sample, you can have some saliva sample, you can have some other samples of human cells, right? There you can apply this RFID tag, and you can utilize those RFID tag for your further process and analysis to identify that particular patient's data. So this is how you can utilize this RFID tag. RFID tags are utilized in the other applications also. Maybe passive, it may be active, it may be semi-passive. This is a typical Walmart RFID tag, which can be utilized for different purpose. Simple security system based on RFID tag you can utilize. You can have the tactile sensor, touch or tactile sensors you can utilize. We have the human body, we can touch a specific object and we can have the feedback from it. Our brain is processing that, and then the data is processed by brain and we can have some activity. So like this, we can have touch sensors and tactile sensors. We can have some 3D visual sensors also, which can be for surface acoustic waves, resistives and capacitors changes are occurring in it, and we can monitor and maintain the XY coordinates of this particular surface. So surface acoustic waves, you can have it for measurement purpose, and tactile sensors are utilized for this purpose. It has a wide range of formulas. Stimuli or applications can be monitored or maintained with a wide range of it. You can see this particular F16 application of a tactile sensor. We have seen so far certain biomedical sensors. You have to remember that what is the difference between the sensor and the transducer. What is the basic definition of a sensor and transducer? We have seen the range of biomedical sensors in human body also for various activity measurement. You can utilize the non-invasive biomedical sensors for skin surface. You can measure it for the biopotential electrodes, strain gauges, thermometers, etc. can be placed. You can classify the sensors in terms of indwelling sensors also, where oral rectal thermometer, then pressure transducers, stomach pH sensors that can be utilized. Invasive sensors we can utilize for this purpose for surgical applications, tissue damage associated with their installations. We can use the physical sensors for measurement of physical quantities like displacement, pressure, flow. For example, if I want to measure blood flow, blood volume, blood pressure, I can utilize certain physical sensors as well. We can have certain chemical sensors which we can utilize, as in when we eat something, we have those food material, and from food material we can have some sensing conditions also. So we can sense the presence of various toxic material, various normal material like sodium, potassium, calcium, etc. using chemical sensors. We have bioanalytical sensors or biosensors, which can be utilized for internal quantities like enzymes, measurement, like antigen, ligand, receptor, antibody, subject, etc. So bioanalytical sensors are utilized for bioanalytical measurements. Then we can have the better sensitivity and selectivity of our sensors for our human body measurement. So this is the basic structure of a bioanalytical sensor. We have the electrical signals, we can utilize those electrodes for this purpose. We have thermal signals, so we can use the thermistor or normalizes for this purpose. We can have certain mass activity, so where we can utilize the ultrasonic devices. We have the optical activities where we can use the optical, photo-optical or photo detectors for measurement of it. And output of this sensing signal will be in terms of electrical voltage, current, etc. that we can convert back into the digital form, and then we can apply it to the microprocessor based system. So basically you can have one sensor, one detector through which you can detect all this system. You can use the bioanalytical system for glucose monitoring, blood glucose monitoring, etc. You can use them for measurement of hydrogen peroxide, oxygen measurement, nitrogen measurement, etc. So those are the bioanalytical sensors which we can utilize for this. We have certain chemical sensors, electrochemical sensors, optical and thermal, and we can utilize those for our different purpose. This is how the amperometric electrode for sensing oxygen works. We have this gold cathode, we have this oxygen preamble member, silver anode, then we have the electrolytic solution here. Against this, we will generate certain voltage over here. So this is how we are generating voltage in terms of sensing signal. That is for detecting oxygen content. Then we have some physical sensors to measure strain, temperature, force, pressure, position, velocity, acceleration, sound, flow, etc. So various electromagnetic field ranges we can utilize for sensing the temperature. As a temperature sensor, we can use the thermometer or thermistor for human body measurement temperature. Thermocouples are utilized for this purpose. The RTDs can be utilized for this purpose. We have seen the RTD, resistance temperature detector, thermistors. Displacement and force measurement can be done through the LVDT, which is linear variable differential transmitter, or we can utilize that strain gauges for this purpose for measurement of displacement of force. Then force can be converted into the equivalent answer, that is M into A. Applications of biomedical sensors in the research, you can utilize these biomedical sensors. You can sense those patient data monitoring system for ECG, AMG, EOG, blood pressure, blood glucose monitoring system, oxygen monitoring system. We can measure the body temperature, blood pressure, blood composition, blood flow, etc. using those sensors. We can utilize those for specimen analysis. We can utilize them for laboratory and clinical purpose also in the medical centers. The complete ICU, ICCU are based on these sensors and its activity. Those activities are being monitored and maintained within this particular electromagnetic radiation spectrum. Now we'll see a typical physiological systems of human body very quickly, where we have covered the biochemical systems, cardiovascular system, respiratory system, and nervous system. So this is a typical cardiovascular system of a patient's heart. This is a respiratory system. So this is how the heart functions. So as in when you take air inside, the lungs will expand further. This diaphragm has its own movement. This typical diaphragm movement is nothing but our force measurement. So there you can utilize this LVDT or the strain gauge itself for measurement of this diaphragm movement. Then you can have the expansion and contraction of this lungs as per the respiratory system. You can have some sound generated during this particular process that we can utilize here, and then we can convert back using that ECG signal. So complete respiratory system analysis, we can have it for cardiovascular system, and each activity occurring within our heart, different section of our heart, we can have it as a part of our analysis. Then we can have a kidney stone analysis. We can use them for image processing technique also. We can sense this image. We can have the photo detectors, ultrasound scanners, and we can detect where the actual body portion of our kidney is having that particular stone, or it is without stone. So normal conditions we can predict, abnormal conditions we can predict. We can maintain the acid-base compositions within this. We can measure and monitor the blood plasma activity within this. We can have the nervous system monitoring, which is called EOG, uh, EEG, EMG. EMG is for muscle. EOG is for electroculograph, that is for eyes. EMG is for muscle, that is for nervous system. So whatever contraction expansion is occurring in our brain muscle, we can have its electrical activity. And this electrical activity we can convert back into the waveform. From this waveform analysis, we can generate that portion where the brain is affected. So bioelectrical potentials are very important for us. Those are bioelectrical potential, resting potential, polarized state or cell, action potential, depolarized or repolarized conditions of those cells. We can have the absolute refractive period, reflective relative period. So bioelectrical potentials we can monitor for ECG, EMG, EOG, etc. And then we can monitor the different activities of our different human body portions like nervous system, brain activity, heartbeats, muscle activity, etc. Electrochemical activity we can monitor and maintain using this. We can use this resting potential, action potential, and we can get the bioelectrical potential graph, action potential graph based on our activity. And this activity can be further classified based on the electrodes which we are keeping. Through these electrodes, we are sensing the different conditions of our ECG, EMG, EEG, etc. And then we can have the complete graph of it from which the doctors can treat a patient. So typically, we can use those transducers, sensors for biomedical applications. We have seen several physical variables, and here they are like force or pressure we can measure using piezoelectric transducer. We can have the bonded or unbonded strain gauge for this particular force or pressure measurement. This we are calling it as a stress or strain. Then we can measure the displacement. The displacement quantity can be measured using the variable resistance, variable inductor, or variable capacitance measurement. The displacement can be measured using the variable inductance or LVDT type of this construction we can utilize. We can utilize the mercury strain gauge for this particular displacement measurement also. The surface strain, we can utilize strain gauges for this purpose. Velocity, if you want to measure, you can have the magnetic inductance principle utilized for this. You can have the temperature monitoring system using the thermocouple, thermistor, ICs, etc. We can monitor the light activity using the photovoltaic cell, photoresistive principle, etc. Magnetic field, we can utilize those CT scanner, MRI scanner. We can utilize those Hall effect. These are the typical diagrams of ECG waveforms, PQRST waves with its ranges, amplitude, etc., and its duration. So this is that human body. Various sensors or electrodes are kept over here. Through these electrodes, we are sensing different signals. Those signals are converted and then it is displayed in terms of PQRST waves. So typical diagram of a ECG transducer for recording purpose, and then finally we can have the ECG waveform of our recorded waveform. And this waveform can be further processed by a doctor. So we have PQRST waves, then its origin, or where it is originated in our heart, how it functions, right? What is its amplitude, etc. in terms of millivolt, that we can plot in terms of a graph, and how much duration it will have as a normal particular patient. So abnormality in this particular amplitude and duration can be monitored or maintained using the PQRST waves of ECG, and then patients can be treated by the doctors accordingly. So this is a typical ECG transducer circuit through which you can monitor and maintain the ECG waveform. This analysis of ECG signal. Further, when you plot them on a scale, on a specific graph, you have a normal ECG waveform like this, PQRST waves shown here. First DVP, AV block. Doctors can very easily identify those things once they see this graph. So this is a typical graph of a ECG signal, and then you can have a bundle of blocks which can be predicted by the doctors. So normal and abnormal conditions of your ECG, EMG, EOG signals can be further analyzed by the specialized doctors. This is a typical diagram of a EEG machine where electrodes are kept here. These electrodes are nothing but your sensing subjects. So this is my subject. Electrode is kept in this particular fashion. Maximum 64 electrodes you can have it as per your requirement. And then this is that ECG signal which is generated from the computer. So this is the typical circuit for schematic diagram of a EEG signal where the human brain activity is being monitored and finally it is shown in terms of EEG. So this is a computerized based system where we are measuring this through the electrodes. Electrodes are your sensing signals. Then it is converted back into our requirements as per the amplitude requirement. Then it is converted into the analog to digital converted form into the digital form. Then it is applied to our microprocessor based system or computers. And through this computers, we are generating this answer, which is in terms of EEG signals of our brain. So various electrodes will sense various signals and then we can monitor and maintain the brain's activity through the EEG machine. This is a typical EEG machine and its output. 8 channels are recorded for a patient data monitoring system and then you can treat the patient accordingly. So nervous system can be visualized, its detailed study can be done and through the various positions of the electrode you can achieve the various signals. Say for example, if I am moving the right hand, right leg, left leg, the activity can be controlled and monitored through this EEG signal. And then you can further apply those to the stress and strain conditions of the muscle activity and then you can treat the patient accordingly. So this is a typical frequency for the EEG band for delta, theta, alpha and beta waves within which there is a normal range and the abnormal range can be above or below this particular EEG frequency. There's a brain waves, alpha waves, beta waves, theta waves, delta waves, etc. So typically you can have this recorded data and this recorded data is nothing but your electrodes data which are kept at different locations of the brain and then you can further analyze this for your own application. So we have a normal range of alpha, beta, theta and delta waves and then whatever abnormalities are there based on that patient conditions, the doctors can predict that and then it can be treated. Same way, EEG signal can be recorded. Then we have a transducers, which are following with the ultrasonic temperature, piezoelectric, pressure transducer, etc. This piezoelectric sensors you can utilize for different purpose. Ultrasonic principle you can use for the flow measurement. So if I want to monitor and maintain the human body blood flow, I can utilize this ultrasonic flow meter. So you can see here that transducer is there here and detector is there. So both this can be a transducer, both of this can be a detector, or one can be transducer, another can be a detector. You assume that there is a flow of certain liquid. For example, in your human body, through artery or vein, the blood is flowing, and you can have a transducer at this location. Now, as and when the blood flows from a artery or vein, this particular transducer applies the ultrasonic waves, and this will be reflected back, and again it will be received at this transducer. So you can find out the total time traveled during this particular period, and then you can scale those things to monitor and maintain the blood flow of our human body measurement. So this is how you can utilize typical sensors, typical transducers for our different human body conditions. So basically, you have to see how you can utilize those things. For example, X-ray. X-ray is utilized for which purpose? For broken bone structure conditions. So if certain bone structure is broken, you take the X-ray image, and that image analysis or image processing of X-ray can be utilized further for that disrupted bone structure. So this is how you can utilize them for our own measurement purpose. So we have seen so far the sensors, transducers, typical type of sensors for measurement of temperature, how blood flow can be measured, blood volume can be measured. Other than this, we have the pH sensors for measurement of pH, conductivity sensors for conductivity measurement, etc. So whichever sensors you want to use, you have to use them in an appropriate range of operation. Then you calibrate them. You identify the location. Those can be invasive or in non-invasive conditions for you. And if the calibration is proper for your system, you can sense those sensing signals. That signals can be further amplified. Maybe in terms of voltage or current, you are receiving those signals. That is amplified further, and that can be applied as an analog to digital converter circuits input. You are getting the digital output. You apply it to the microprocessor based system from where you are having the feedback. So patient data monitoring system occurs through all these principles of your sensors and transducers. In your ICU, ICCU, complete patient data monitoring system is based on this various sensing system. And you can record them, you can store them for your further process. You have the robotic surgery now. In terms of robotic surgery, whatever actions are there being operated by doctors, robots can be trained accordingly, and complete surgical process can be done through the robotic arm. So you can have that open heart surgery or kidney stone analysis and surgery through the robotic principles also. So this is how you can utilize them for our human body measurement and control purpose. So we are ending here. We have seen so far sensors, transducers, its applications, various graphs of ECG, EEG, etc. If you have any doubt or question, you can ask me.
Okay. Thank you, sir. Thank you so much for giving your precious time.
Thank you.
No questions from the viewer side. I think students have no doubt because sir had covered all the things in detail. Sir, is there anything else you wanted to cover before a wrap up?
No, this is okay. Because we have a
Oh,
critical time, we have to stop at 1:30 because
okay,
otherwise I
okay,
can
sir.
continue up to 3 o'clock. Yes, I don't know.
Okay, sir. So great. Thank you, everyone. We appreciate you being here. Thanks to Parul University for giving me an opportunity to host such kind of webinar. Thanks again for joining us today. We will see you next time. Thank you so much, sir.
Thank you very much, madam, for inviting me. Thank you. Thank you, faculty members. Thank you, students.